Welcome everyone to this mini ZIO conference we put together at the last minute, it seems. So I'll kick this off with a talk about which I was supposed to give at Functional Scal and could not because of an illness. But so this talk is about how I write production grade and cloud native microservices with ZIO. And not just with ZIO, but with the ZIO ecosystem as a whole. So when I did some research for this talk, I reviewed some well-known guidelines about how to write resilient and well-architected apps. So one of them is a 12-factor application. I put these links here, and when I post the presentation, you can look into them. But the 12-factor application, it's a pretty good set of guidelines on architecting applications. And in fact, I linked to an update to that set of guidelines. And I chose a few of the guidelines there to discuss in this presentation. And the other one is cloud native apps. Now, cloud native is something we hear quite a lot these days, usually around Kubernetes or applications running in the cloud. But there's actually a pretty good set of guidelines that Microsoft has put together about how to write applications that work well with platforms like Kubernetes and cloud providers. So what we will discuss today in this talk is how can we put together a configuration for our applications that's layered, that's coming together, that's being composed from several sources. How do we provide observability for our applications using structured logging and metrics? And the other pillar of observability is usually tracing, usually considered to be tracing, but I won't talk about this today because I've not had a chance to use any of the tracing libraries for ZIO yet, ZIO telemetry, but those exist. And then we will discuss resilience, which is also a pretty significant pillar for cloud native applications, and disposability. So let's start off with configuration. So something to know about configuration, particularly in complex applications and in microservice environments, is that configuration is not just a file that we load and read at runtime. It's not just one file, at least. So configuration can be divided into, at least in how I see it, to three main categories. So basic configuration, like batch sizes, number of retries, stuff like that. That's usually just constants that we don't want to stick to hard code in our code and be able to easily modify them. So we just move them out to some sort of configuration file, and they usually are unchanged throughout the life of the application, but they're there and they need to be loaded from configuration. The other part is environment-specific configuration. That's usually pertinent to where are we running. This is sometimes called service discovery. So the most stark example of this is what's the host name of our Postgres database and what port is it running on. And this is something that's coming from the environment, and it's not just specified in our configuration. And the last part is sensitive information like credentials or tokens. And every one of these categories, they need to be loaded differently. And we'll see examples of these soon. So ZIO config lets us go from this case class to a way to load it from configuration pretty easily. Both to it lets us go from a description of this case class of how to load it to a configuration, and it lets us take that description and also render it as documentation. But I won't discuss that today because it's not quite relevant. But given this case that describes how we connect to Postgres, we can right now see that there are three categories of information here. So the first one is the service discovery part, right? The host and the port. That's exactly what I described earlier. So these are coming from one source of information when we run our application. The database, that's more the basic configuration part. Well, it kind of depends how you see it, but the database is more of the basic configuration part. It's we usually always work with the same with a database named the same way, but it still needs not to be hard coded, right? Because maybe at some point in the future we'd like to change that. And finally, the credentials. Well, these are secrets that need to be loaded from a third place. So with ZIO config, well, we can obviously write a descriptor for describing how to write, how to read this sort of case class from an arbitrary source of configuration. But if we're running on Kubernetes, for example, then the service discovery part will usually be loaded from environment variables. So if you've ever used Kubernetes, you know that whenever you deploy an application to Kubernetes, then Kubernetes will inject environment variables that describe where to find other services running in the same cluster, the same namespace, into the environment of all pods running in the same namespace. So we can, instead of reading the host and the port from these entries, we can tell ZIO config, well, you need to read them from these entries, from these environment variables. And once we've specified the names of the environment variables, then we can actually later tell ZIO config to read these from the system environment. And this is possible. There are a bunch of very good examples on the ZIO config documentation, but this is the gist. You can specify a source for every component of the case class that you're loading. And similarly, we can do the same thing for the other components of the config. Well, we can tell ZIO config to load the database from some sort of type safe config file that we've loaded, and the username and password can be loaded from JSON credentials. So, for example, if you're again using Kubernetes or even using secrets manager from AWS or any other secrets management solution, you can load a JSON payload remotely from that service and tell ZIO config to read it using the from operator. And finally, once we have this descriptor in place, then we can just convert it to a layer using the read function from ZIO config and converting it to a layer. And that's pretty easy, because all we had to do is specify the sources for our configuration, and then we just executed the read operation, and ZIO config put everything together for us, reading the configuration from all the different components. And obviously, we've got good error messages as well, because if ZIO config fails to read the component from one of these sources, then it will tell us that it failed to read it, and we will know exactly what failed and why. So the ZIO config really makes our lives quite easy when reading layered configuration for our applications. So that's configuration. The next part we'll discuss is logging. So it's usually said that microservices are cattle and not pets, in the sense that we just treat them as perishable resources, and whenever one of them perishes, we just replace it with another one, unlike pets. And the other thing to know is that because we are expecting such large amounts of instances of microservices, no one will be actually reading the individual log messages that we're logging from the applications. Unlike applications, in a few a few years ago, where it was, I don't know, it might have been more common to read the log messages. Well, these days nobody actually reads the individual log messages unless trying to diagnose a particular problem. The only thing that's actually reading these log messages are machines or services that take the log messages and extract metrics or information from those log messages. Services like CorelLogix or Datadog, they can take our log messages and extract metrics from them that we can later view on graphs and view as summaries and do analytics on and so forth. So maybe the important part to understand here is that the individual log messages are not as important as the aggregate information that they describe. So, given these 3 lines that describe some things that happened for a particular customer, if we'd later like to extract some sort of metric or aggregation from these lines, obviously we'd be having a pretty hard time because the customer ID is specified differently in each of these log lines. So I don't envy the data engineer or the SRE responsible for later extracting information out of these lines, but they're not going to have a good time. So obviously structured logging is the solution for this. So ZIO logging under the ZIO organization, well, ZIO logging lets us annotate a block of processing with some sort of annotations, of logging annotations. So given, a method that fetches a customer info, and we're performing a log message here, we can use the locally method on ZIO logging to apply an annotation for any log messages emitted from within this block. So what we're doing here is that we are extracting from the request context the customer ID from a header. And once we've got that customer ID, then we can annotate any logging messages that are emitted in this block with this annotation. So this is super useful. And now these logging annotations, they're strongly typed. They're specified as instances of a log annotation data type. And it's not super ergonomic yet, the API. I have some ideas on how to improve this. But so like you have to specify a merging function and a default function and a default value, which is, I think it's not essential to the API, but nevertheless, once you've defined the log annotation, then you can use it throughout your application, and you have the guarantee that when you're formatting the log line, then the type here will be the type of the data annotated by this log annotation. So once we have this log annotation, then we can use it like we've done here. But it's like a function that is applied to the contents of the annotation. So we're applying the log annotation to the customer ID that we've extracted from the request context, and using it to annotate the log messages here. So once we've done that, then we can later render our log messages with some actual structuring. So we can actually specify a section here for our log messages that has a key and a value for every annotation. And this is, in a sense, the ZIO take on MDC, on mapped diagnostic contexts, except that MDCs never work properly with async applications, but this will work very, very consistently. And obviously, we can later render the entire log line as JSON and convert this text here to to a JSON object that is later processed by our log management services. But that's the general idea. And it's very useful to be able to emit structured logging out of your applications easily. And ZIO logging lets you do that. I also looked at a few times before at Logstage from Izumi, and it's really slick in that it lets you just extracts the structured parameters out of the log messages for you if you use their string interpolator. So I'd like to give a shout out to that here, but I've not had a chance to use it in production yet. Okay, so even more important than logs or metrics, because like I mentioned earlier, we can use our logs to extract metrics like, what's the request rate for a given customer? That's something that can be extracted from logs. And services like CoreLogic or Datadog, they do that for us. But even more importantly than logs, well, we can just emit metrics directly from our applications. Things like latency, error rates, these are super important. And ZIO metrics, another library in the ZIO organization, well, that gets us from 0 to exposed Prometheus endpoints with metrics quite quickly, and with a pretty decent API. So let's see. The first part for implementing metrics using ZIO metrics, well, the way I do it is that since every component and module in your application is going to have some sort of set of metrics, then I think it's pretty nice. It's a pretty nice pattern to just create a metrics case class that contains the data types, the metric data types from ZIO metrics inside your application module. So inside our module here, the API endpoints module, we've specified an errors counter, a query latency histogram, and a gauge for counting how many running requests do we have right now. And we can create these metric data types by using the constructors from ZIO metrics. And every one of these gives you a ZIO that requires a metric registry. So you see that we've put these 3 data types together using a for comprehension. So we construct the errors counter, we construct the histogram, and we construct the gauge for running requests. And then we put them all together in this case class. And then we convert this ZIO to a layer to make its injection easier to other parts of the application, because you'll see in a moment that we are going to request access to this metrics object instance through the ZIO environment. And whenever we're requesting things through the ZIO environment, it's usually easiest to then provide them to the rest of our application using layers. So let's see, how do we instrument a function that we have in our application using this metrics instance? Well, we start off with this get customers function, which runs DB query, and then filters the list for accounts with the requested status. And you see that it's a task, so it might fail with a throwable, or return a list of customers. So first off, we need to request access to the metrics instance. So we do that using ZIO.service, which will yield the metrics instance, and will add this service wrapped in has to the environment. Now, so that means our return type has changed. And now we can start instrumenting the various parts of this function. Well, so the first part, and probably the easiest, is just to count the errors. So whenever we have an error on this DB query, then we use tap error to increment the counter on the metrics instance. That's fairly easy and not quite as intrusive as the next 2 metrics. The next part is timing the query latency. So we can time the query latency using the time underscore function on ZIO metrics' histogram instance. And this function, what it does is it just wraps an existing ZIO function with its instrumentation. And whenever this ZIO effect completes, then it will log its duration into the query latency histogram. So that's the second metric. And the last one is the running request metric. Now, what we want to do here is when we start the execution of this function, we'd like to increment the gauge, and when we're done, we'd like to decrement the gauge. And that's this when we want to wrap two actions around a given action, that's usually a bracket. So what we're doing here is that we're incrementing and using bracket underscore to decrement the running request gauge when this action here inside is done. And now I know you're probably thinking, well, we can't see the forest from the trees here, right? Because we started off with this small and very elegant function that just ran a DB query, and now we've got all this noise around it. So I think this can be improved. And since we're working on ZIO ZMX at Diverge, Adam specifically, I think we have some cool avenues of improvement that we can do there. So for example, an aspect-based API would make this much nicer because we can keep this function as is, and then we can, after the fact, append some instrumentation aspects on top of it. So we can count the errors with this errors counter, and we can measure latency with this histogram, and we can measure the active executions with this gauge. And I think we might look into this in ZIO ZMX. We've been interested in bringing aspects to all of ZIO. I'll talk about this in a few slides, but this would make the API much nicer because you can literally focus on the business logic and then visually see the added instrumentations on top of it. And probably this can be done for a ZIO logging as well, when we like to annotate a block of information, a ZIO block with some added parameters. So those are metrics. Okay, the next one is resilience. And by resilience, I mean resilience to failure. Now, failure, when we're writing microservices or any sort of distributed system, failures are inevitable. We should always expect them. And ZIO includes a very elegant and composable and super expressive retrying facility with ZIO schedule. But there are some other more sophisticated, you could say, resilience patterns. So again, the Microsoft handbook for cloud native applications includes a very nice summary of these patterns, and other libraries like Resilience4j and Hystrix from Netflix before it, they aggregated a bunch of these patterns in convenient libraries. And obviously we need something tailored and native to ZIO, which uses the environment and other ZIO data types and so forth. So well, I'll show in a moment a library that implements these common patterns of retries, circuit breaking, bulk heading, and so forth. Some of these can be found in ZIO itself, but the more sophisticated ones like circuit breaking and bulk heading, well, these are found in the resilience library with Z. It's from Steven Vroonland, S. Vroonland on GitHub. I'll provide a link at the end of the presentation. And it's a really fantastic library which provides composable resilience strategies. I'll show how they compose in a few slides. Beyond providing the actual components of circuit breaking and bulk heading, which we'll see in a moment. And it also provides a very good best practice retry schedule moduled on an article from Amazon Web Services. I didn't include it because the slides were already quite long, but it's there in the documentation. So what components does resilience provide? Well, First, it provides circuit breaking. Every component in resilience is basically a function that wraps an existing ZIO action. So if we are provided with the circuit breaker for our function, then we can just wrap a DB query with that circuit breaker. And this type parameter here describes which types of errors are considered breaking for the circuit breaker. I didn't include any sophisticated examples, so you can refer to the documentation for resilience, but it's pretty cool and lets you design some very sophisticated circuit breaking facilities. So if we're provided a circuit breaker for our function, then we can just wrap it with the circuit breaker, wrap our DB query with the circuit breaker, and we're done. And now the type signature resulting from that is a bit of a mouthful, but it really lets us differentiate between an error resulting from the circuit breaker itself and an error from the DB query itself. So it's really quite beyond beyond the length of the signature. It's quite a nice use of ZIO's typed error facilities, and this really lets us handle things differently. So another part of our application can return a different type of error to the user if the error resulting from this part of the application is a circuit breaker error. So it's really nice to be able to differentiate between these errors. Right, so that's a circuit breaker, and the way you construct it is using the make constructor, which gives you back a managed. Now, why is this a managed resource? But well, it's a managed resource because it has some stateful functions to it, and it has some resources that it allocates, like a fiber that resets the circuit breaker every now and then, and these need to be obviously managed. So that's how you construct it. Another interesting component provided by resilience is a bulkhead. And a bulkhead is, you could say it's a, well, the name comes from freight ships, where they would divide the contents of the ship using some sort of isolation mechanism, so that if water came into one of the parts, then it wouldn't drown the ship entirely. It wouldn't spread to the rest of the ship. Well, in the same manner, using a bulkhead, we can guarantee that this function would not be called concurrently more than allowed by the bulkhead. And subsequently, if it would be called concurrently more than allowed, then it would drown out the rest of the resources of the application. So the bulkhead allows us to limit the concurrency of this action. And beyond, limiting concurrency, which a simple semaphore could do, it also prevents queuing. So a semaphore, if you would just wrap DB query with a semaphore, then other parts of the application would just queue up in the waiting for a permit from the semaphore, and eventually consume memory, all the memory from the application. So the bulkhead allows you to prevent that. It also has a parameter for controlling what's the maximum size of the queue of fibers waiting for execution for this action. So it's really, if you've ever used a semaphore to limit concurrency to one of the parts of your application, you should really consider using a bulkhead instead, because it's much more resilient, so to speak. So you use this bulkhead the same way, and it also results in the same long type signature, which I did not include. And now we get to the nice part of resilience. Usually you want to combine these two components, right? You want circuit breaking and you want bulkheading. So resilience, the library, lets you create composable policies, composable resilience policies, or strategies, or whatever. The way these are composed is that we create the circuit breaker and the bulkhead, and we convert them to a policy, and then we compose them. So whenever we use the composed policy, that's like applying both of the components on an action. So you would use this policy, which has the type parameter which describes which errors it handles, the same way you would use the bulkhead and the circuit breaker. You just wrap the DB query with that. And in the same manner, it gives us the policy error, which tells us whether this is an error from the resilience mechanisms, or is this an error from the underlying action that we're doing. This is really sweet. This means that we can design composable resilience strategies for our entire application, and we don't have to repeat ourselves or pass along 1,000 components to our signatures. This is really cool. I love it. And I really recommend using the resilience for any application that needs to handle errors. What we've seen so far are these cross-cutting concerns, right? Things that we just wrap over the business logic, and they don't modify the business logic itself. They just modify some auxiliary property of the execution. So resilience strategies, metric instrumentation strategies, tracing, logging, these are all cross-cutting concerns, and we've seen that all of them act like wrappers on top of ZIO actions. And the general pattern for this is an aspect. And Adam gave a pretty sweet talk about aspects a while ago. I put the link here, but you can also just search YouTube for it. And I recommend you watch it. And at some point, you can bet that we will be bringing aspects to most in ZIO later on, in ZIO 2.0 for sure. Okay, so we did metrics, we did logging, we did configuration, and we did resilience, and we've got disposability, which is the last one. So in the 12-factor app, disposability is described as short startup time, graceful shutdown whenever there's an error. And what I've added to it is shut down the app whenever there's an error in a background process, like a Kafka consumer or whatever. So let's talk about the first two. So the first two are basically handled for us by ZLayer. So if we've got a bunch of dependencies in our application, like a Redis connection or Postgres connection and a Kafka producer, if we've described all of our dependencies as ZLayers and then provided them to our application using provide custom layer with the concatenation of these layers, well, ZLayer will take care of initializing everything in parallel and destroying everything in parallel and guaranteeing that everything is actually destroyed. So the Redis connection is torn down, the Postgres connection is torn down, the Kafka producer is torn down and flushed, and so forth. So basically, we've just by using ZLayer, we've sped up considerably or not considerably, depends on the application. We've sped up the setup of our application startup because we were initializing everything in parallel. We're not waiting for Redis to respond and then Postgres and then Kafka. We're just running everything in parallel and then starting the application. And we've got graceful shutdown done correctly because ZLayer guarantees that everything is destroyed properly. So that's, if you've done ZLayers, you've got a whole bunch of benefits that are just there for you without having to do much work beyond using layers. That's good. What else? The other part is background processes. Now, background processes actually need quite careful management because we need to make sure that they keep on going in the background, and whenever there is an error in one of them, that we crash the entire application or stop it or start it or whatever. So let's say we've got a background worker and a Kafka consumer, then the naive way to run them in the application would be to fork them into the background and then run a ZIO.never action to just wait for them. Well, this won't work correctly because if the background worker crashes, then nothing will watch it. So that's not going to cut it. So instead, well, we could await them. We can await the worker and the consumer using ZIO zip. This is not going to work either because if the consumer crashes before the worker, we're not going to see it until the worker finishes, and the worker never finishes. So basically, the Kafka consumer might crash and will never restart during the lifetime of the application. Okay. What's the actual solution for this? Well, the actual solution for this is using race-all. So we can use race-all to basically watch all the fibers for all the background processes that we're running at the same time. And if any one of them, for some reason, exits prematurely or exits with an error, then this entire ZIO action will end as well. I should have added a map ZIO done here, but I'll add the fix before I publish the slides, because we actually want to crash the application if one of these crashes. So anyway, now with this pattern, what happens whenever we add more and more processes, so if we're adding more consumers, then we have to remember to run them, to add them to the race-all list. And obviously, the compiler will complain if you add one of these fibers to the for comprehension and you forget to add it to the race-all list. The compiler will complain if you forget to add it. But you know, I think it's not super elegant the way to do this. And I promised streams. So my solution for this is to actually use streams merge all unbounded operator. So this is kind of, if you've never used streams, this is kind of surprising because there's no actual streaming operation here. We're just converting effects to a stream and then merging them. So what actually happens here is that the merge all unbounded operator will just run all of these streams concurrently and wait for them to do something like crash. And if one of them crashes, then it will crash the entire stream and cancel all the rest. Now, what we're doing here is that we're converting every background work, every background process to a stream using from effect. And then we're draining. So by using .drain, we're saying, I don't care about any outputs from this stream. I just want you to run it. I don't care about what it outputs. So that way, we tell merge all unbounded to just start running all of them concurrently and don't emit anything because we don't care about the outputs. We just want them to run in the background. And what merge all unbounded basically gives us is the implicit racing all. Right? Because whenever one of these crashes, they will immediately crash the merge all unbounded operator, which will cause the rest of the streams to be canceled. And subsequently, the fiber running these background processes will be canceled as well. So that's my solution to this problem. Obviously, if you've got a small number of background processes, then this solution works quite as well. But I think this works more elegantly and scales better for larger amounts of competence. So to summarize, we've seen layered configuration with ZIO config, structure logging with ZIO logging, and metrics with ZIO metrics, and ZIO ZMX in the immediate future, and resilience with resilience with Z, and disposability using ZLayer and ZStream. So that's all I have, and I'll be happy to take questions offline on Discord. Thank you, everyone.